Today I've got a Maxon EC Max 30 60-watt brushless motor. It has motor power wires, 3 brushless motor, and Halls. And at the moment I do not have the encoder connected up yet. So we're going to take a look at Hall velocity. This little motor can do like 10,000 RPM on 24 or more volts. So we're going to check out how to do some high-speed velocity control in a velocity mode. So today we're going to use the ACJ. It's a small brushless servo drive that can take Halls and encoder if we had it, but today it's just Hall velocity. So let's see how to wire this guy up. The DC power supply, HV ground and HV, and frame ground. So you'd connect the frame ground here. Plus 24 volts or 48, and ground here on J3. The motor signals on J2. If there was a shield, you'd connect the frame to pin 1, but I just have UVW on 2432, and if there was a ground wire to the chassis, you'd connect that up here. The feedback is plus 5 with respect to ground. Hall, UV, and W are hooked up. I'm going to wait to get my differential encoder and hook that later, so just Hall velocity today. The winding is the 272763. I measured the resistance, 1.26 ohms of the winding resistance, and I can tell it's this winding here. So this is the data we'll use to enter into CME2. And you can see the wiring diagram for motor power, red, black, white. Plus 5 on green, ground on blue. Hall 1, 2, 3 will hook up to Hall UVW. We'll wire in a logical manner and then do phasing. So looking at CME2, we can see the basic setup screen is a brushless rotary motor, just Halls, no encoder yet. Velocity analog command, that's typical for velocity. And I'm going to switch from just pure trap commutation to estimated sinusoidal. This will make things more efficient when we go faster. And I'll use Halls for velocity because it's pretty good. If I'm trying to do slow speed with Halls, that's not very good. It's going to be a bumpy ride, but maybe we could get somewhere with low speed using the back EMF. And that's the setup for the basic setup. So off to the motor data. So I've got units here for the it's grams, centimeters squared. That's we do it in kilograms, so move the decimal point over 3 places. It's 1 pole pair or a 2-pole motor, so it's got 1 electrical cycle, a north and a south magnet. I've got peak torque in millinewton meters, 0.458 for a millinewton. Just move the decimal point over, and the continuous torque here. There's a max theoretical speed, about 15k RPM. We're never going to hit that with 24 volts. And a torque constant, again, millinewton meters, move the decimal point over. And the back EMF is 393 RPM per volt, so 0.393, move the decimal point over for volts per k RPM, invert that, 0.524, and that's about right. The back volts per radians per second matches the newton meters per amp, so that's a good check. And the volts per k RPM works out 2.5 volts per 1,000 RPM. So based on this, we got a feedback of 6 counts per rev. It's, not very many counts per rev with just Halls. The encoder will bring that up later. But we can calculate the initial tuning values. This will give us the continuous current, peak and continuous. This is right out of the spec sheet here, 2.66 amps. And initial values for CP and CI. We can check the bandwidth, but I've selected max speed here, so when we go fast, it's going to use all the voltage to give us speed. So 600 hertz of bandwidth is pretty low, but it's a 2-pole motor, so let's say 10,000 RPM divided by 60 is 166 cycles per second times 1 electrical cycle, so 166 hertz should be sufficient for this. So I'm just going to leave that current loop calculation alone. And for phasing, I use the manual phase, tools manual phase, apply a current. When I go forward, I'll see that the indicator leads whether I go forward or reverse. Everybody gets a chance to deliver current. You could do a little bit more current if you want. So for example, when I first got this motor, it had a wicked lead forward and a wicked lag backward, so the red indicator lagged. I tried to give it 60, and that just made it worse, so I gave it minus 60, and we get a good lead in both directions. So that's the phasing. Now we're phased to the hulls, and when we do the tuning with the CME2 scope, we can take a look at the velocity loop tuning. We'll take a quick peek at the current loop. So here's the current loop. That's the calculated values. Looks good. A little bit of quantization. It's a higher current drive, so that makes sense. Another note here is the enable input was hardware disabled, and the default is pulled down to enable. So we can do that. You can have a switch on input 1 to do that too. So that's how I enabled the drive. Anyways, back on track here. We're going to do the velocity. This is a percentage of the rated. I'm just going to do this slow. Maybe change the time a little bit. Trigger's good. Velocity parameters, that's a good accel and decel. 1,500 maybe was too much, but this should bang back and forth a little bit here. So we can see the motor actually moving forward and reverse here. It wiggles a bit. I got a little overshoot. See, my gain was, my integral was turned off. Probably still get a little overshoot here, but I would probably not get to steady state. That's not bad. The integral is good for getting rid of steady state error. I could try to take this down a little bit. That might be a little softer. It doesn't seem to matter here. These calculated values were about 15,000 too. That's a little stiffer. I noticed when I was going slow, it liked a little less gain on the VP. So I'll leave that alone. So when I tune this velocity loop, I actually want to look at the operating speed that I want to go at. So I'm going to change my trigger type here. We'll do a couple of seconds of trace. I'll do current actual to take a look at the actual current, and voltage limit warning, event status, voltage limited. I do not want to be in a voltage limit very long and very hard, and I will hit a trigger of rising edge, let's just say 1,000 RPM, and that will be from my command. So I'm going to try the jog here. Let's do 2,000 RPM, and we'll give it a little spin here. So we're running 2,000 RPM on the control panel. We can see that. I got a little overshoot. I'm not at steady state here. I got some steady state error, so I'm going to turn my integral on hard. Probably don't want integral when you're stopped or trying to control zero, because Hall velocity is really bad when you're below like 500 RPM. But the steady state error, there it goes. We saw the jiggle. So when I stopped, it had the jiggle. So we can turn the integrator down a little bit. Maybe that'll reduce the jiggle. That was a little smoother. Takes a little longer to get into speed, but that's okay. The current seems to be fairly low. It's a no load condition. So I'm going to try some higher speeds here. So there's 5,000 RPM, and let's try 9,000. All right, sounds a little funny. Seems to be doing it. Can I even get to 10,000? All right, we're hitting a voltage limit. There we go. So that's too fast. This motor's not rated for that for 24 volts. 9340. So let's do 340. Still hitting the voltage limit. So let's dial it back down here. See, we got a little headroom on this. Not much. If you had a load with current, you'd have some IR drop. So, don't over-design your system. A couple amps at a few ohms is going to need a couple of volts. My power supply is only 24, so maybe we need to run this with a 48 volt supply. It's fine. Current loop, the inductance is low. The ripple current shouldn't be too bad. But I think we can give it a go with this. So when you're all done tuning and testing out, don't forget to save the flash, and then you can also save to a file just this whole configuration. You could save a motor data file if you want to just save this, but when I get my encoder, I'm going to go back to the basic setup and redo this again in position mode. So just some quick comments on cabling, grounding, shielding. I'm using a B&B 232 9M USB from B&B Electronics. This is the Copley serial cable kit, which is connected to the control port. This is ACJ-SR, so it's the serial cable kit for the ACJ. It's a little unique from the other drives, but this is a really small drive. On the back of the drive, you'll notice there's a Berquist plate. One side's got the circuit board on it. The other side has the heat plate. This needs to be connected to the frame. When you screw it down, that heat plate gets connected to the frame and finds a good path to earth. So I connected earth to that just to keep the PWM noise from infecting anything. The Hall inputs are not shielded, but Hall circuits have filters inside the drive, so the PWM noise gets filtered out. And these cables are not shielded either. It's not good to have cables like this for the most part, because it is a PWM amplifier. So my recommendation is to get some shield on these cables and not couple them up with a feedback device. On the back here we have a heads 5540A11 encoder on the back of the shaft here. My new buddy Anthony managed to mechanically get this connected. It's brilliant. But this is a single-ended A, B, index, +5 and ground encoder, and we're going to get a single-ended to differential converter from US Digital so that we can hook up differentially to the feedback device here. And that cable must be shielded, and the frame of that feedback cable should be connected to earth there. So there's more to come on this, but that will be position mode with encoder, and this is just Hall velocity. Good for going fast, not very good when you go slow. Thanks for watching.